Da war das so ganz gut. In der Pause gemacht. In der Vormann hat zusammen noch so Fenster und so. Und dann kam er so auf den Boden, jemand Bescheid gegeben. Manhood. Ja. Okay, we need to talk about something. First of all, hi. Second of all, so I wrote something from the board. So I want to let you know that it's important to know that next week there will be no lecture on Thursday. The lecture will be moved to Wednesday at this hour in this room. And for that, there will be no exercise session. So this is our last exercise session for this year. And I brought something. So pass it around. If you have any other questions, with what you think. Yeah. So today, the format of the exercise session will be a bit different. And so I will talk about a solution technique for macroeconomic models that has not been introduced in the lecture yet. It will be introduced tomorrow. So the problem is that I'm a bit faster than Rita. So yeah, we'll have to kind of work with that. But I prepared a set of notes which I have uploaded. And what we will do is we will go through these notes together. I will try to introduce the solution concept. We'll answer any questions you have. And then I've also prepared a set of
Can you pause?
that we're going to go through together. But I do not expect you to have to solve that problem set, obviously, because it's something that you'll first introduce.
Thank you very much.
And I think that the benefit of this is that I think Rita will introduce the concept tomorrow, yes, but from what I've seen on the slides, it's not a very detailed introduction. So I think that maybe for you it's also good to have seen this beforehand so you can follow the lecture better. If after this week you feel completely confused by the fact that I've introduced something that was not in the lecture, let me know, and next year I will, or like for the next exercise session, so for next year I will try to time better. Okay? Okay. So have you looked at the set of notes that I've prepared? Yeah? Okay. So you know the existence. So the concept we will talk about is log linearization. Has anyone heard about log linearization before? Thank you. I guess not. It's fine. So if we take a step back and if we think at the models that we have talked about so far, we have always done all the maximization problems. We have written down the equilibrium conditions that characterize our model. For example, that would be the Euler equation, the cardinal accumulation equation, this and that. And it is quite clear that some of these equations that characterize the solution are nonlinear. And what do I mean by nonlinear? I mean that somewhere in that equation there's a multiplication or a division or an exponent and stuff like that. And from now on, slowly, what we will also do is we will introduce some shocks. Shocks are, for example, a productivity shock. For example, a new innovation happens that we could not predict and suddenly our economy is more productive. Or, for example, I don't know, there's a government spending shock. So Friedrich Merz goes tomorrow and says that, you know, for a month, I will reduce VAT to 5%. predict. But when you solve your model, you account for all the future periods that are coming towards you, right? For the ones that you have to plan economically. And if you know there's going to be some shocks that we are not aware of, you have to form some specific expectations for those shocks. And for that, you will see in the future models, we will have these expectations of breakers here and there. So, we will have nonlinearities in the form of multiplication, exponential subsets, etc. And we'll also have expectations. And if you end up with a model that has nonlinear equations and expectations,
Sorry, I cannot.
you will figure out that there is no explicit solution. For example, I cannot tell you that consumption at time t equals 5 is, I don't know, 100,000. And for that, we need to find a way to, what do we do if there's no solution? We approximate one. We figure out how to get close to the solution that we think that should be there. Okay? And what we also did, if you think back at these models, we have written down some steady states. Does anyone have a good indication what a steady state is? With or without model? Yeah.
In case of steady state, all our components, like for example, consumption, capital stock, grow at the same rate.
Yeah, exactly. So essentially, we have a steady state where we know that all the agents are behaving optimally, and in addition to that, if you have no growth, forget about growth for a second, we are not changing our consumption level or income level or whatever. And that's a steady state. It's a state in the economy where there are no shocks. Everything is at plateau. Okay? So we know what the equilibrium conditions are, and we know the steady state. And empirically, some smart people figured out that if you have business cycle frequencies, for example, the next couple of quarters, or like next 2-3 years, your economy does not change that much. It just fluctuates around the steady state. You know, there will be a shock, it will increase your consumption for a bit, but then that consumption will again go down, because it was a temporary shock. And that's what we will be using in order to solve our models. What we will do is we will take,
No, just regarding last exercise, where we learned that an increase in consumption can be attributed to an increase in the depreciation rate, right?
Yeah.
Okay. So if the consumption was to drop, then there would be a positive shock that the depreciation rate had fallen.
Yeah, for example, that would be a type of shock. And if it doesn't drop permanently, if it drops for a few quarters, then you will see that when that depreciation rate goes back to the initial value, your economy will also go back to its steady state, you know? And that's what I'm trying to get. I'm trying to say that if we're talking about business cycles, which is what we're after, we're not talking about long-term economic growth right now, we're talking about business cycles. So what's going to happen today if I do something to the economy in the next couple of quarters? Then I can use my nonlinear equations and my steady state. And because I know I will be moving around that steady state, I can do a linear approximation of my model around the steady state. Okay? So imagine, for example, you have imagine, for example, that you have your consumption over time. Okay? This is long-term consumption. Or it looks something like this if you plot the data. Okay? If you plot the data for consumption, it's going to look something like this. If you take out the long-term path, which was this, if you remember at some point we were talking about the HP filter, which was the trending stuff. It was taking away the long-term growth. And it was, if you had plotted it, you would have seen that one of it was like a linear line going up, and the other one was like, it looked like this. You would split it into long-term growth that looked like this, and then something like a component that looked like, you know, an EKG thing, you know. Those are business cycles. And let's think that this is our steady state. You know? Some days will be above our steady state, above that horizontal line. Some days will be below. But this is a linear thing, right? So what you can do is you can approximate your function, turn it into a line, and then find the points that it fluctuates around. Okay? So this is what we're going to do. And once you write your model in terms of deviations from the steady state, everything becomes linear. All the equations that you have, even the non-linear ones, they become linear. And when you know from your math class, if you have a set of linear equations, you can solve them just fine. Okay? So this is what we're going to do. And for that, we need to learn how to linearize these equations first. And then once we have the set of linear equations, you will see in subsequent lectures and exercise classes, there is then solutions to find out how consumption will move, how investment will move, how the interest rate will move. Okay? But first of all, we need to linearize those things. And that's what we're going to do by log linearizing. Okay, so let me show you how I would do what I just said in math. Okay, so goal is write everything. And by everything I mean equilibrium conditions. In terms of deviations from the steady state. Okay? Let me go through some notation first. So, you have a variable xt. Okay? This could be consumption, this could be investment, this could be, I don't know, hours worked, whatever. We will denote the steady state with a bar above this variable, okay? Steady state, this variable is x bar. And notice it doesn't have a time index because in the steady state time doesn't matter. Tomorrow and today, my x will be the same. Okay? So, this is the steady state. Okay. How do I write this in deviations from the steady state? The deviations from the steady state will be, for each variable, denoted with some sort of wiggly hat. Okay? And this is a definition, so I'll use this three line here. So, it tells you that a deviation from the steady state is essentially given by, first of all, that deviation from the steady state, how far up or how far down I am. And then you divide it by the steady state. And what this will do is it will tell you that now that xt hat, you can interpret it as percentage deviations from the steady state, which is useful if you're trying to interpret economic models. Does that make sense? Like this definition? Okay. And then what you will do is, you can also write this in terms of log deviations. What I will do is just, I'll just take the logarithm of both sides, okay? Sorry, I will take the logarithm of the right. Okay? That's another definition. Let me write this out of it. split my my fraction here, okay? I take that fraction and I split it into two parts. Notice that the second logarithm is the log of 1, which is equal to 0, because it's essentially x bar over x bar, that's 1. And what remains is the logarithm of this fraction, which can be rewritten as log of xt minus log of x bar using standard logarithmic definition. Okay? What this tells you is that the deviation from the steady state is essentially defined as the log of whatever value my xt has minus the logarithm of the steady state. And this is equivalent to that. And why do we use logs? The good thing with logs is in the future you will see if you have multiplication and you if you take the logarithm of that multiplication, it turns everything into linear again. Okay? Function for linear one. Like how can you approximate a nonlinear function in a linear way? Right, yeah?
Taylor approximation?
Perfect. Okay. Does everybody know the Taylor approximation? Have you looked at it? No. Okay. Where are the math people doing this? Don't call it math. So anyway, the Taylor approximation is in order to turn nonlinear functions into linear ones. Okay? What it does is, for example, if you have a function, and it's clearly a nonlinear function. I can approximate my nonlinear function around a point, which I will call x bar, in a linear way. Okay? And the Taylor expansion will give me the formula for that. And as you can see, if I move sufficiently small around that point, my function is linear. Okay? So I am allowed to do that. This is one approximation. And I have to stay sufficiently small around that point, sufficiently close to that point. Otherwise, I might end up here, and then it's not a good approximation anymore, because obviously here would be my actual value, and I would approximate with this. It's not a very good approximation. But if I'm approximating around this area, then my actual value is here, for example, and I'm just approximating this. It's okay. It's sufficiently close. Okay? And for that, Taylor, which was a mathematician, wrote down a formula. He said that for any function f of x, where x is the argument of that function, you can write it in linear terms as, first of all, around the point that you're approximating. You need to evaluate your function around the point that you're approximating it. For example, this here, it would be my x bar. And then you need the first derivative of that function with respect to x. And you need to evaluate that first derivative around the point which you're approximating. And then you need to multiply it with the difference between all of your x's and the x bar. Okay? Just take this as given. It's an approximation method. It works. And we're going to use it to approximate our function. Okay? Let's do some examples with this Taylor approximation so we can get more. Okay. Example. Say my function is called f of x of t and is equal to x of t. So essentially, whenever I give this function, it gives it back. Okay? How would the Taylor approximation of this function look like? Notice that here, this should be, it should not be an equal sign, it should be a approximate. Right? Because it's not approximation. Okay. So, going back to this. How would I use the Taylor expansion to approximate this function? What would I do first? And I'm obviously approximating it always around an x bar. So it's any x that you can think of. In our cases, the x bar would be our steady states, right? Because that's what we said we would do. We approximate our equilibrium conditions around our steady state. So, what would this look like if you take the Taylor expansion? Yeah?
It would be x bar plus 1 times xt minus x bar.
1 second, you were a bit fast. Okay, f of x and t is x bar plus
The deviation, which would be 1 here, so
deviation is not 1, the derivative is 1.
derivative, sorry.
Perfect. Okay? So this is how you would use that formula to approximate this function. And remember at the beginning I told you that I would like to write my variables in terms of deviations from a steady state. And if you think back at how I define these deviations, you will see that I have this part, but I don't have this part. So I would like to slightly transform my equation so that I can write it in terms of deviations from the steady state in this sense. So what I will do here is I will divide both terms, which I can do, it's like factoring out, by x bar. Okay? Factor out x bar. This would give you that it's x bar 1 plus this, and then over x bar. And this is exactly the definition that I wrote down at the beginning of the class. Okay? And I log linearize this one. Okay? Does that make sense how it is? If you don't get this, yeah.
So the question, for what types of functions can you think about using the approximation? So in your notes you say, I think, sufficiently smooth function.
Yeah, for example, this method doesn't work if you have a kink. For example, your budget constraint might have a boring constraint. And that would, if you plot your function, it would be something like a step function. Like this. Okay? For a certain point, you're not allowed to go below this. But in this class, we will not deal with everything I give you is going to be log linearizable. Okay? But in general, there is models with non-differentiable functions, and then this method doesn't work anymore. You need other methods. Okay, example 2. You can do this also if you have functions with more than one argument. For example, let's think of a function with more than one argument. Let's just say it's the multiplication between these two. Okay. is the steady state. First of all, you start by evaluating the function at the steady state. This would be this f of steady state. What is the steady state? Yeah?
X bar times y bar.
Yeah. It's just the function without any time indices and with a bar. Okay? And then if you have two arguments, so two different variables, you need to take the first partial derivative for both of them. So this would be, if you take the derivative of the function with respect to xt, then that would be f of x would be just y t evaluated at the steady state is just f on y bar is just y bar. Okay? So this is y bar. This is the first part. And then what is the second part? It's the deviation of the variable with respect to its steady state. And that variable should be the one you're differentiating with respect to. So this time would be x. Okay? I'm just applying the formula above, but for two variables now. Okay? And then the next one, the next part that you should apply this to is the partial derivative, but this time with respect to y. Okay? And it's going to be the same. So it's going to be this time x bar. And then what is the variable with respect to which? What is the variable with which with respect to we're differentiating is y. So it should be the deviation of yt minus y bar. Okay? And then remember I said I want to write this with respect to so I want to write this using the definition of the deviation from the steady state. So again, I will have to somehow divide this over x bar and this over y bar. Okay? Because now the definition is incomplete. So what I will do is I will take out xy bar as a common factor. Okay. And then it would be y with this y cancels out, this x with this x cancels out. What do I have? I have x, y, 1 plus deviation of xt, and then y t deviation. Okay? And that's purely, I just took the definition of this that I gave you before, at the beginning of the exercise. Okay. So this Taylor method, you can see it can get quite ugly very quickly if you have a lot of variables. Because you always need to remember, okay, which variable am I differentiating with respect to, okay, which now is the steady state, and what is the partial derivative evaluated at the steady state. The good thing is, if you have purely multiplicative functions, where there is no plus or minus in any part of the function, there's a second method, where you just take logs of both sides, and then you just subtract the log of the steady state, and essentially then you apply the second definition that I'll show you in terms of log deviations. Okay? But this applies only if you have purely multiplicative functions. If you see a plus or minus, forget about this method, okay? So. Let's see, for example, take the function xt is equal to yt times gt. It's just a function, okay? So whatever I'm going to show you now, treat it as a cookbook. If you see a multiplicative function, you can do the exact same steps that I'm showing you. Okay? Step 1. Take logs of both sides. So it would be log of xt. And the log of a product is then, you can also write it as the sum of the log of each of those variables, right? Log of AB is equal to log of A plus log of B. So this is going to be like this here. Plus log of B. This was step 1. Very simple. So, step 2. Write the steady state in logs. Okay. What is the steady state of that function? Yeah? Sure? Yeah, exactly. So it will be x bar is equal to y bar times z bar, right? And then again take logs of both sides. It's equivalent to log of x bar, log of y bar, plus log of z bar. Step 3. Subtract from the equation in step 1 the log of the steady state. Okay, so it would be log of xt minus the log of x bar. And then from this side, you do log yt, you just write as d, plus log of zt, and then you subtract the steady state, which is log of y bar minus log of z bar. Okay? Okay. Does this, what I did just now, make sense? Why we do that? Like, why it's okay mathematically to do that? So, what is this? What is this expression here? Yeah.
So log of xt over x bar.
Yes, and if you think of the definitions I gave you at the beginning,
And it's xt hat.
yes. Xt hat. And this minus this is y hat, and this minus this is z hat. I have everything in log deviations now. I log linearities. Just by doing this simple mathematics that are just like taking the logs of and then subtracting the log of the steady state. And every time you see a function that is purely multiplicative, you don't have to think about the Taylor expansion, just do this. Step 1, step 2, subtract the steady state, and it works. Okay? But this, as I said, works only if you don't have any addition or subtraction. Otherwise, it doesn't work. Okay? So, I also put in my notes a third method. It's called the substitution / exponential method. I personally don't use that method because for me it's a bit, it can get confusing very quickly for me. So if I see a plus or minus, I just do the Taylor expansion. If I see a multiplication, I just do this, what I'm just showing you, the log method. But I will show you this substitution method. Feel free to, if it clicks for you and you feel like you can solve things more easily, feel free to use it. Okay? And the substitution method is more flexible compared to the log method because it works also if you have addition or subtraction in your function. And I think it's a bit less technical than the Taylor expansion, but then you have to remember some things by heart. Yeah, you decide if it works for you. I'm going to show it to you, and we'll take it from there. So, substitution. So, as we said, this is our definition of a deviation from the steady state in logs. And this can be rewritten as, if you just take this to the other side, it can be written as log of xt is equal to xt hat plus log of x bar. If I take the exponential of both sides, take exponential of both sides, I'm going to end up with e log of xt e xt hat plus log of x bar. So if you have an exponential where the exponent is a sum, you can also rewrite it as a product, right? So this would be the same as writing down x a plus b. This is the same as x plus a times x plus b, but just for the exponential function now. E this times e log of x bar. Okay? So e raised to the power of log. This is essentially just xt from your standard rules of exponents and logarithms, etc., etc. xt. This remains as it is, and this is again, this simplifies to x bar. Okay. And then there is an approximation saying that e to the power of u for a small u can be approximated by 1 plus u for small u. So now I can approximate my function like this: x1 plus xt hat. Okay? And this is essentially the same thing that I did with the always ended up with this using a different mathematical. Yeah, it doesn't make sense, right? So yeah, anyway, I used it using different mathematical approximations. Okay? But this just shows you that if you want, you can use this. Wherever you see a function that has a variable xt, you can remove that variable and write this. And this will, and then replace this e to the power of xt with this. Okay? Let me do an example. So, again, xt is equal to yt times zt. And again, the goal is to write this in deviations from the steady state. Okay, if you had to use the substitution method, what would you use? What would you replace there for xt, given what I've just shown you? Yeah?
X bar times 1 plus xz.
Yeah. Okay. Notice that xt is equal to x bar times e to the power of xt like this. Zt is also z bar times e to the power of zt, zt hat, and yt is equal to y bar times e to the power of yt bar, y hat. Okay. Substitute all of that. This is the same as writing x and now use that e to the power of u is equal to 1 plus u. Okay? Essentially, I'm just doing what I just did in the interaction of this method, but now with multiple variables. Z remains as it is. I just replace this e to the power of z hat. Okay. If okay, first of all, remember that is given by x bar is equal to y bar times z bar. So it's like saying that a is equal to b. If I divide both by a, it will be a over a. That's 1. B over a is also 1, since they're equal, you know? So if I divide this side by x bar and this side by x bar, I get rid of them, okay? And I just have that 1 is equal to 1. So x bar, okay, divide everything by x bar. By x bar. So it would be 1 plus xt plus 2 plus yt. This is times z bar are equal, so it's up here. And what I have is that it's 1 plus xt equal to 1 plus yt. I need to multiply those two out. What do I have? Plus then zg bar hat plus yg zg bar. Notice that these deviations from the steady state are very small. This would be something like 0.01 times 0.02. For approximations, this is negligible. You can just ignore this. If you see a deviation multiplied by another deviation, these numbers are so small, they don't make any difference in your approximation. So this is equivalent to, this is almost equal to 0. Okay? And then this one cancels out. xt is equal to xt hat is equal to yt plus 0. Okay. And this is actually what I also got with the log method. If you look up. But yeah, how many steps did it take me with the log method? How many steps did it take me with this one? That's why I said I don't really use this method, because you have to remember, then you have to multiply things out, then you have to see, okay, this is small, I can ignore it, blah, blah, blah. So I don't use this method. But if in cases you find this method useful, feel free to use it. I'm still going to show you guys this one. Okay. These were the notes that I wrote down. And then I also prepared a problem set with 5 equations that need to be log linearized. 3 of them are multiplicative, so we can use the log method. 2 of them have addition and subtraction, so we're going to use the Taylor expansion. Okay, so you get to see everything that we've just done right now. At home, feel free to, if you find the substitution method helpful, feel free to try redoing the exercises with the substitution method to convince yourself that you end up at the same result. Before I start the problem set, are there any questions?
Yeah, so I don't understand what we're doing yet. So
Makes sense.
could reiterate how many steps there are? I
So
mean, it's always the same steps, right?
Yeah. So let's just ignore the substitution method for now, okay?
Yeah.
Let's go back to the log method. So, if you have multiplicative functions, there's 3 steps that we need to follow. Step one is you take logs of both sides of that function. Okay? You just write down your function in logs. That's step 1. Then what you do is you write down your steady state, and then you take the logs of the steady state. Okay? That's step 2. And then you subtract the second equation from the first one. Okay? So if you have those 2 equations, you subtract the left-hand side with the left-hand side from the second equation. So log xt minus log of x bar. And you subtract the right-hand side equation with the right-hand side equation of the steady state. Okay? And this will give you the definition of the log deviations. Which is here. Okay?
Because this is the deviation of xt
xt?
from x bar.
Yeah, in logs.
Defined as the steady state.
Yeah. And that's what you do. And then you have your function, which was a multiplicative function. Now you have it linear in terms of deviations from the steady state. And if you do that for all of your equations in your model, then you have a set of linear equations and you can solve it.
How do we get the numbers and values for the state?
You solve for them. Have we solved so far? Anyway, when we do the RBC model, we will calculate the values for the steady state.
Because so far it just means that we just add this
Yeah.
bar on top
Yeah.
and we just say let's.
But we will look at that. Anyway, nowadays, there's software obviously calculating the steady state for you. You don't have to sit down and calculate x is equal to 3. But we will also do it per hand and you will see how it calculates, okay? But we haven't done that yet. It's not relevant for this test. You just know that there's a steady state. We set it equal to x bar, and then you subtract it from your equation. Okay?
And so the goal is just to linearize the function.
Linearize the function, yeah. And I said that if you have any function that is additive or you have subtraction somewhere, you cannot use the log method. You need to use the Taylor expansion. Okay? We'll do that if you look at the problem set, we'll do that for equation 4 and equation 5. Okay? Okay, I think maybe if we do some more examples, it will become clearer. But I think it helps if you just use this as a cookbook and you apply it to your function. Don't think of too much about why it makes sense. It just makes sense mathematically. So just use it for any function that is given to you. Okay? If you see a multiplicative function, do the log method. If you see an additive function, use the Taylor expansion. Okay? And just take it as a cookbook. Yes?
And what then do the hats, are these estimates or what do they represent again?
So what it tells you that at this point in time, your x is, for example, if this is 0.2, it's 20% above its steady state. So consumption tomorrow, if today is the steady state and we do something like in the economy, we have a shock, and the deviation of consumption from the steady state is 0.2, it means that consumption relative to the steady state has increased by 20%. Okay?
So that the hat is just this thing where we subtract the steady state and divide by it.
Yeah.
To get the percentage deviation.
Yes.
So,
And it tells you, for example, that this variable, if you know the deviations of these two variables from the steady state, you can calculate the deviation from the steady state for this variable as the sum of these two. So if these two go up by 1% together, 1 plus 1 is 2. So imagine this is consumption, this is the deviation of the steady state for the interest rate, and the deviation of the steady state for inflation. And then you add them together, and it tells you if you know that the interest rate increased by X%, and this by Y%, and this is Z%, then consumption increased by the sum of those. And then you know what happens in your economy if you have a shock. Okay, if you have a shock to this, for example. How does it affect this?
and there could be n additional
Yeah, every measure.
right?
Yeah. Is it clear now?
Yeah, as long as the function stays multiplicative, right?
Yeah, so otherwise you need to use the Taylor expansion around the steady state, but then again we get a similar form. You will get again something similar. Okay? If you want, try this multiplicative function, try to log linearize it using the Taylor expansion around the steady state. You will see you need to adapt to this. Because the Taylor expansion always works. Okay. And just a hint, or like, I don't know, advice. The first time I saw this in my master's, I was super confused for weeks. So it needs a lot of practice. You need to sit down and do it again and again and again. And at some point, trust me, your hand will do it on its own. Okay? Let's start with problems and try. So the first equation that we need to log linearize is the Cobb-Douglas production function.